Hi, and I've got a question for you. What do you get if you cross a snowy holiday with the principal chip scientist at Nordic Semiconductor? An A to D taped out on tiny tape out by Carsten. Hi, Carsten. How's it going?
Hi, how's it going? It's going
Yeah,
good.
great to see you in an interview call. Normally used to seeing you on the YouTube channel.
Yeah.
Tell us briefly about the story of your snowy holiday.
Right, so it actually started right before the holiday. So I got to learn that on the Tiny Tape Out 6, there was the option of doing analog. And then we got in touch somehow through YouTube, LinkedIn, something. And you mentioned if I had any sort of designs ready. And I first thought, no, that's way too much work. I don't have time for that. But then I had holiday. We have a concept called winter holiday here in Norway. So I went up to the mountains with my kids and brought my computer and actually had some time to code on my SAR. So this is a design that I had from, well, way back when. And actually, I guess last Friday, I was able to complete it and then submit it. And yeah, a really fun story.
Yeah. So you've already done a video about an hour long, really going into the details of the SAR, and it's a fascinating watch. And there's a paper as well. So if you're interested to find out all the gory details, then check out the video, which I'll link above somewhere. And on this video, I wanted to more kind of get to know you a bit as a person and ask you some difficult questions.
Good.
So I hope you're ready. And yeah, looking through your CV, which you posted online, it's amazing to be talking to the principal IC scientist for Nordic Semi. Yeah.
Well, thank you.
Yeah. And you're kind of been involved in the NR51 series analog design and all of that.
Yes. So I started in Nordic 15 years ago, right after my PhD. So I usually say it's my first and only real job is in Nordic Semiconductor.
Yeah.
So most of the time been working on analog design, but then I led the wireless group for about 7 years. But then now moved back to a more sort of technical role where, I have the nice title of being the IC scientist.
Yeah, it's a cool job title. And for me, it's really interesting because you're obviously very high up in the industry. And you're also really interested in the idea of open source semiconductors. So that's really what I wanted to talk to you about. So yeah, why open source?
So I guess it started, I should also mention that I teach at the Norwegian University of Science and Technology. So I'm there 20%, 1 day a week, teaching a course on advanced integrated circuits. And that's really because we see from Nordic side that we need more analog designers. Over time, we need them to be educated, and that's sort of why I've joined in at NTNU. And when I saw, I think this was 2021 probably, when I discovered the Skywater PDK. And I've been looking for that type of opportunity because I've been working on closed source type of, or closed NDA type of PDKs for a long time. But my interest really lies in how do we make analog circuits? How do we simplify that? And that's quite hard when you only work on closed source PDKs and also on binary files. So the fact that now there was this open source PDK, there was the Magic tool, which I love the fact that it's text files. There was XGEM, which is also text files. That enabled me to actually port the work that I've already been doing for about 10 years over to Skywater and really get going and sort of go all in. And I think it's an interesting ride.
Yeah. Maybe this is a good point to ask you how the professional tools compare with the open source tools.
Yeah. So I'm kind of have the opinion that all the professional tools are expensive, very expensive, and they're kind of not that good because they don't have that many users. I mean, what we do when we make integrated circuits is quite a specialized skill, which means that the tools are not that great because not many people use them. So what I like about the open source tools is that, well, of course, they're not as polished as the professional tools, but they're free. And a great thing about them is that you don't have any blockers for innovation. So anybody can add anything to the simulation tools or to Magic or whatever. So when it comes to comparison between open source and professional tools, I don't necessarily think it's sort of a direct comparison. So if you compare Magic to Virtuoso, Layout Excel, or that type of, I guess, the normal standard, then of course Layout Excel is better. It has more features. It has schematic-driven layout. It has a lot of those sort of features to simplify the day, but you can still do the work in Magic, and that's cool.
One day we'll get Airwires for Magic and XGame, and that will be really great.
Yeah, or we go the finally maybe get the automatic analog layout to work. After, I don't know, 30, 40 years of trying.
Yeah. Okay. And does Nordic Semiconductor endorse your efforts in open source semiconductors, or is it like a completely side part of your equation?
So I would say that Nordic endorses my working at NTNU and then working with the open source tools there. I would say that within Nordic, I know we have multiple employees that use the open source tools, but not really as part of the standard sort of IC development. Of course, the trigger for that is as soon as we can see that we can actually do a part of the job in the open source tools, then I think it will happen because it's free. I don't know if that answered your question, but...
yeah, partially. One of the other questions I had was, what obstacles do you think there are for open source silicon? So maybe we could just split that into two and say, what obstacles do you think there are for the open source tools within a company like Nordic?
So I think there's a couple of things there. First of all, it has to have the PDK that we're actually interested in. So we decide on technology based on, usually it's costs. So Nordic is in sort of the not the ultra low cost, but pretty low cost type of system on chips with radios. And there it's picking technology that is correct or right for us. And of course, then the tools need to have support for that type of technology. But let's say that we actually assume that we're doing something in Skywater, then I think what's blocking us now is the trust. So can we trust that the models are good? Can we trust that there is no, what should we say, bugs in the tools? And I think we can build up that trust by actually doing what we're doing now in the open source community and with Tiny Tapeout, sort of iterating on designs, iterating on tapeouts, finding problems, fixing them, and so on.
Yeah. And as a kind of broader picture, like outside of Nordic, what do you think? What other obstacles? What are the kinds of things that people say why they think that open source semiconductor tools can't work?
Well, I think there's a lot of opinions out there, and but when it comes to blockers, things actually preventing progress, I think many of them have been removed by the fact that we now have the open source PDK. We now have the full sort of flow is there. It's possible to tape out. And the fact that the work that you're doing and others are doing to sort of making it accessible and cheaper, that's really a good thing. So now what I think is blocking us is, well, it's not really something blocking us. It's just a matter of time. Now, hopefully it's with enough people, with enough effort, we will make it into viable professional tools. And I'd love to see that day, because I'd love to encourage my friends in the EDA industry to improve a bit, to get a bit challenged.
Yeah. Well, your point about it being more open to innovation or fixing bugs or documentation or things like that, that's a really great point.
And it's cool to see. I didn't know actually that we had the possibility to do co-simulation of digital and analog. And that's something I saw from your RDAC with, I think it was Verilator and then NGSpice.
Yeah, it's a new feature of NGSpice, yeah.
Exactly, and that's the type of thing that's actually hard in the normal EDA tools also. So, yeah, we have an opportunity here to really improve, I think.
Great, yeah. So, question kind of on the Skywater open source PDK. Do you think, is there And the way, and your experience inside Nordic, choosing the right technology for the product. Do you think there's a industrial use case where Sky 130 would make sense, or is it mostly only for education training purposes?
So let me speak on the 130 node as in general. Because back in the day when we did the NRF51 series, which was a quite often used Bluetooth type of product, that was actually 180 nanometer technology. So it is possible to do quite complex system on chips in a 130 technology. I think these days the type of industrial products that would be that would fit well would be maybe power management circuits, maybe energy harvesting circuits that require a bit higher voltage, and not too complex system on chips. So definitely there are possibilities there. Also the fact that Sky 130 has an RM feature, which is cool, that makes it an interesting technology. But of course, when it comes to competing with the lower scale or the nanoscale technologies, it becomes a bit difficult, because if you have millions of gates, digital gates on your design, then it's probably not going to be the right technology. But for analog, I would say it's the last comfortable node is 130.
Okay, that's a nice way to put it. Yeah, yeah. And I'm finally putting some effort into my own analog journey and taking inspiration from your great YouTube channel.
Great, thanks.
Yeah. And your book as well, I just discovered from your website. So we'll link that in the description.
Yeah, there's a new version in progress now, because I'm teaching the course now, which means I'm iterating on all the chapters.
Yeah. Great. Yes. Okay, so what other questions did I have? Here's one. So, and it's kind of a good segue, is I'm just starting on my journey now. And one of the things that makes, in my opinion, analog a lot more difficult than the digital stuff is maybe the digital is more fully automated. So we have the open lane flow. There's more than open lane as well. But typically you put your RTL in and you get a GDS out that is ready to tape out. With the analog, it's like you need to be familiar with 4 or 5 tools. And for each tool, they're all quite different and they all have their own secrets. Put it that way.
Yeah.
What would you suggest? How would you recommend a newcomer to get started with analog?
I think the first thing to realize is that it's going to be a lifelong journey. It is not simple. And one of the reasons it's not simple is because it's dealing with the real world. Analog is the interface to the real world on integrated circuits. Now, digital, we've made this fantastic abstraction that there is something called a 1 and a 0, right? And then from there, we can do almost anything and be certain it's going to work. That's not the case for analog. You do something and most of the time it doesn't work. So I think getting into analog, it's about, of course, learning the tools, trying things, but also learning the transistors, the solid state physics, and realizing and be comfortable with that you will not know everything and things will go wrong. But that's also fun. As long as you don't care about the money, then you learn something new. When I was looking through your book and your website, there's a fair amount of philosophy in there, like life philosophy. Do you think that part of you is kind of what makes you a good fit for analog, or do you think that you've had to learn that because of your profession? No, I actually do believe there is sort of a fundamental difference in personality, at least if you look at the mean analog designer versus the mean digital designer, or the average digital designer versus the average analog. I think for analog designers, they're more comfortable with not knowing and sort of this uncertainty, and it doesn't really matter that much. All rules are guidelines for an analog designer. While if you sort of put it in a box, I find that digital designers maybe like things to be structured and organized and to know things. And that's possible in digital design, while I don't think it's necessarily possible in analog design. So I have this philosophy that there is a slight difference in personality, and maybe that's what draws us to the different areas. But of course, this is correlation. It's not necessarily causality.
Causation.
Right? Causation. That's the word.
I think it's a great point that you make about the abstraction, and it's something that is very easy to forget that you're doing as a programmer or as a digital designer. You just take that 1 and 0 concept as a a real thing. And then it's only when you start getting into simulating the transistors that you realize, no.
Yeah, and all the work that we do in OpenLane is really to ensure that assumption is still true.
Yeah, and that you can leverage being able to write one line of Verilog that instantiates 10,000 transistors and never even know about it.
Exactly, yeah. And that's where the hard part about the analog is, I think. I don't think it's that easy to find those abstractions. You kind of have to deal with the physicality of the thing.
Know which rule of thumb to use at the right moment.
Yeah, and when they don't work anymore.
Yeah, when you can stop trusting it. Yeah. Which does happen. Like, I think you still have these things with the digital side, like metastability, that is easy to think that is not there until it bites you. And then you have to understand that, you do need to pay attention to some of these kinds of things. But most of the time, you can get away with even making terrible RTL and it still works. Ask me how I know. Okay, great. So those were most of my questions. We do have a couple of other questions from people I asked who were interested to ask you some things. So one question comes from someone who's beginning with analog design, and they want to know how to close the loop with a mixed signal design. Where you have to design to iterate. So any comments on that?
Yeah, so I think it's realizing that in analog design, right, you start with the schematics, and then when you're happy with your simulations, you run all the different temperatures, you run all different voltages, you run all the different transistor corners and resistor corners and capacitor corners. At some point, you decide now it's a good time to start the layout. So you draw again the same thing, and then you extract the parasitics, and then after that, you have to simulate again. Now, if it doesn't work then, what you actually have to do is go all the way back to schematics and then start again. And this is where analog design really can take a lot of time, because those loops can be quite long, days, weeks, months. And I've experienced some designs that have been maybe 10 times through this loop. So that's kind of the reason why in my SAR, and sort of the idea behind the SAR, is to get to the layout as fast as possible. So you actually just skip the simulation on the schematic and you go straight to layout. But of course you have to get the layout then. So when it comes to mixed signal, then usually it's sufficient to consider it as two separate blocks. You have your analog and you have your digital. As long as the interface between them is relatively well defined, then it's possible to make a model of the analog system in the digital with a Verilog. And as long as you hook it up correctly, it'll be fine. The challenging parts come when you have tight feedback loops, like in all digital PLLs or in some ADCs. There you actually have to co-simulate. Simulate both the digital and analog. But like I think you made an RDAC, right, for your tape out. That's kind of a case where you have a digital section and you have an analog section, but you could actually just model the digital stimuli as a piecewise linear function in SPICE if you wanted to, and get maybe enough information about the analog performance.
Yeah, my XGEM just uses pulse transient generators at half frequencies to generate all the codes to drive it one cycle. Yeah.
And that might be good enough. I think the hard part about analog and mixed signal is you can do a lot of things, but not everything will give you value. So sort of that's where the experience comes in, is this something I actually have to do to make it work? Maybe.
Yeah.
But then, of course, I should mention also that usually when you get the chips back, you can be surprised that things can go wrong.
Yeah. A whole new set of issues to care about. But maybe that's like why it seems to me that analog designers start off with a much better defined spec before they even start working.
Yeah, that's usually necessary, because if you make an LDO or you make a power management system, you kind of have to know, for example, how much current it's going to draw. And if that changes, let's say we get to the end, we've done our layout, and suddenly somebody says, oh, but it wasn't 30 milliamp, it was 100 milliamps. Then you have to go all the way back to the beginning.
Yeah.
So as you go through the analog process, changes to spec is quite costly because you've already proceeded down a quite locked path. You can't change the transistor sizes that easily because you have to move everything on the layout around. While I think on the digital side, you really work up into the RTL, and you could also work up until the GDS, and then you can iterate, right? Because changes in spec is quite easy.
Yeah, you might start with an 8-bit wide data bus because that makes it faster to simulate or whatever, and then eventually it will just be a parameter and you'll flip it over to 16 and just rerun the flow. And
exactly, yeah.
Related to this, there's a question about the machine learning, the AI layout, because I've seen a few startups promising to reduce analog layout time by basically learning from previous. I mean, I don't really know how they plan to do it. Do you think that's gonna make an impact into analog layout design?
I think the hard part there is finding enough data. So we know
it's not
that
published.
Exactly. So, I mean, the data for layout will be with companies. So maybe the big ones like NVIDIA, they have a lot of layouts internally, and they have a lot of AI stuff they can train or models they can train on the layout. So maybe for some big companies it is possible. But for example, if I was Nordic, or I am Nordic, and we had an AI that could actually be trained on our layouts, then I wouldn't want to give that to anybody else.
Yeah.
Because there's so much of the skills are actually in the layout. So I think that the availability of good data is the challenge. But maybe we can fix that with open source. So let's see, yeah.
Yeah. Okay, so here's a good one. What is there anything that you can do if you don't trust the SPICE models?
Yes.
If you don't trust the PDK very much?
Yes, there is. And that this is something that happens quite often, at least in the early days of a process. First of all, you have to trust your brain. You have to trust your knowledge about solid-state physics, such that if the models or simulations tell you something that you feel is wrong, maybe I'm right. Maybe my brain is correct. But quite often, we do trust the models, and then we tape out, and then we get the chips back, and we discover, well, something is weird here. I've experienced that a couple of times where we actually see behavior that is not covered in the SPICE model. And then we basically have to iterate. Because as soon as we understand the physical phenomena for why it goes wrong, we can usually find a fix in the design that sort of prevents it from happening. Yeah. A good example there is there are multiple different types of noise sources, like thermal noise, we have flicker noise, but also in some technologies we are starting to see what's called telegraph noise or burst noise, which is a slightly different statistical phenomena, but that is not in a standard sort of BSIM 4.7 SPICE model. So there you actually have to know that it's there, that type of noise is there, and you have to put in circuits to alleviate those concerns.
Even though you wouldn't even see the result of them in the simulation, maybe?
Yeah, you're basically simulating blind, but you know that for the real circuit, it's going to be a good thing.
Well, that's real deep inside knowledge. I guess that's the kind of thing that you build up with years of experience.
Yeah, and it's sort of an exploratory journey. You have to like the mystery of it. You have to love the fact that things go wrong, and you want to figure out why.
Back to the philosophy. Yeah. Yeah. When I was reading your paper, the phrase state of the art struck me quite a few times, and it just made me think, it's like, where does that phrase come from? State of the art. It's like a technical thing, but in technology, we're often a bit kind of, we want to push the art away, and we want to do everything with computers and equations.
Yeah, but there's still beauty in electronics, I think. There's a beauty in both digital and in analog. I think for analog, the beauty can be in the schematics, can be in the layout.
In the layout, yeah.
Yeah. The beauty of digital is definitely not in the layout, because that's just a random mess. But it can be in the architectures. It can be in the RTL. Yeah.
Yeah. Yeah, that was one of the first people I interviewed about analog layout was Thomas Parry at Spherical Systems, who's doing like satellite stuff. Right. And he did a PLL that looked to me great because it had this kind of fourfold symmetry. And one of the things he told me was that with analog, if the layout looks good, then that's a good sign.
Yeah, I agree to that.
Yeah. So maybe let's end the interview with a couple of stories from your experience at the coalface. Tell us some things that went horribly wrong, or were broken tape outs, or wasted millions of dollars.
So I won't take all the stories, but I do remember a couple. There's one from very early on in my career, and this was actually not a design that I worked on myself, but we were sitting in the lab. We knew that the ADC inside the chip, it had a gainer, but we didn't understand why. And we had tested everything up and down and so on. And in the end, we were sort of lost for what to try next. But I remember pushing the PCB, so just pushing the edges of the PCB. And suddenly I could see the band gap sort of drifting up and down 100 millivolts. And then you just go, wow, why? And then you start searching and searching and searching. And inside we discovered that there happened to be a current mirror, PMOS current mirror, where one of the transistors was this way, the other one was that way. And it turns out that when you stress a PMOS, due to something in the solid state physics, the mobility of holes, the majority carrier in PMOS, actually have a different behavior depending on the direction of the stress. So the current goes up on one side and down on the other side. And that type of failures, well, of course it should never been rotated anyway, but this is sort of call it a mistake that happened one day for one person, and unless you have something that discovers that mistake, then it hits the market. And that's kind of the thing about analog design. When you do it in industry, you have to have sort of layers upon layers with safety nets. Because also, since there's a lot of money involved, as you mentioned, there's tens of millions of dollars maybe involved for the most extreme nodes. That's a lot of responsibility to put on one person, which means that you kind of can't. You can't have a junior designer designing a block and then being responsible for $1 million mistake. You have to put in safety nets. But I do remember one of my own sort of really early mistakes was I was working on the ADC on the 52 series, the peripheral ADC. And this was the first tape out. So we always do sort of a number of tape outs before we hit the market. But on the first tape out, I was testing the ADC, and for some reason, a lot of current went into the input. And that shouldn't happen. But every time the clock sampled, there was a lot of current going in. Traced back to, turned out I had used the wrong transistor in the schematic, such that in the sampling switch, where I was trying to be clever and switching the bulks of the transistor, I was actually connecting the input directly to the substrate, because it happened not to have a deep NMOS layer underneath the transistor. And at that time, this was a relatively fresh technology, so we didn't have the check in the LVS deck at that time. So these type of things happen. But my experience is that it's usually the simple things that really gets you. It's not the things that you worried about for the key performance. It is the inverter that you forgot to check, or the logic gate that you forgot to check, or the two's complement that happens to be offset binary, and those type of call it stupid mistakes that always happens because we are human.
Yeah.
So,
nice. Thanks for sharing.
Yeah.
Any last remarks?
I maybe on that point, because you have to become slightly comfortably numb when you're an analog designer. It's like that. Is it a Pink Floyd song called "Comfortably Numb"? Or at least it's
it
one.
Does sound familiar, but I don't know where from.
And that's something I used to tell them, because I hired analog designers for quite a few years. I used to tell them that you have to become comfortably numb, because you will make mistakes, things will happen, and you still have to proceed and actually make something. You have to fix it, move on, and not worry about the millions of dollars that go out the window, because that's somebody else's problem.
Yeah. Well, that's a nice message to end on. So if you're thinking about getting into analog design, don't worry about making mistakes. Just go on and do something cool anyway.
Yeah. Innovate.
Innovate. And join the open source revolution.
Yes.
With us.
Come and have fun.
Yeah. Well, thanks very much for your time, Carsten.
Thank you,
Super
man.
appreciate it. And looking forward to seeing how well the A to D worked that you taped out.
Yeah, me too.
Yeah. Great.
Thank you.
Thanks a lot.